Hi everyone, welcome to your Calc 2 review, which is essentially MAT 266 exam 2 review. My name is Vedang and I'm the executive tutor, and I have with me Suryansh, and we're located at the Pulse Tutoring Center, so essentially ECG 152. Well, welcome. Before we get started, this is where you can find the review. When you search up math.asu.edu/mat266, you'll have a window open that's going to show you where you can access the review. And in this case, it's the MAT266 exam to review, right? So, four things stand out to me before approaching any Calc 2 problem. And the first one being read the problem slowly and circle the givens and you know what you're asked to find. Whatever your preferences are, if you like circling the givens, if you like underlining the values, or if you like rewriting whatever is given in the problem again so that you're not missing out on anything, I would highly recommend that you do that. Number two being define your variables and write the function or equation that models the situation. For example, you can include the domain and any units if they're important. Number three, your calculator must be your friend, not your enemy. I've seen countless times where students know the right process or know the right steps, but don't know how to input it into the calculator, right? You need to set it up in a way that is intuitive for you. Also, make sure that you practice problem solving using the same calculator again and again and again, because the more you familiarize yourself with how you're using it, I think the better you can handle it. And number four being interpret your answer in context. Check units. Check if it makes sense. For example, if you're calculating the drag of an aircraft or the lift of an aircraft, it cannot be negative, right? State your conclusion, make your assumptions, write them down clearly, and see if the value is reasonable. Right. Thank you for joining me, and now I'll give it on to Suryansh to cover this part.
Thank you, Vedant, for going over what FSC Pulse Tutoring is and where the exam to review for Calculus 2 can be found. I'm Suryansh. I'm a tutor at the FSC Tutoring Center, and I tutor MAT and Industrial Engineering courses, and I'll be going over some questions from the exam to review. So to begin with, our first question, they have given us a Laplace transform function in terms of integral, and they're asking us to find the Laplace transform function when f of t is equal to 1 and when f of t is equal to e power 2t. The way I found it is because they have given us that L of f of t gives us this integral on the right. So that must mean that f of t in part A is equal to 1 and f of t part 2 is equal to e power 2t. So to begin with, I am going to replace all the f of t on my integral with 1 for part A, and I get 0 to infinity e power minus st times 1 dt. Now, this is an improper integral because it has an infinity in the bound, so I need to convert this in terms of limit. So then I get limit of a tends to infinity. The integral goes from 0 to a, my a to the power minus st dt. After that, all I have to do is take the integral now. So upon taking the integral of the function, I get limit of a tends to infinity minus 1 by s e power minus st. And its bounds are from 0 to a. So I will plug in my bounds and essentially get limit of a tends to infinity minus 1 by s e to the power minus sa minus of minus 1 by s e to the power minus s of 0 because my lower bound is 0. Um, then I can plug in my a to the infinity since I've done with my definite integral. So my next step here would be minus 1 by s e to the power minus s times infinity because I've accounted that limit a tends to infinity. So I'm just replacing my a with infinity now. And this becomes minus 1 by s e to the power minus, uh, or just e to the power 0 because s times 0 is just 0. Um, so this first part here, e to the power minus s infinity can be written as 1 by e to the power s infinity. And this is essentially 0 because my denominator becomes infinity. So this function becomes 0 and e to the power 0 is equal to 1. So then I'd have 1 by s. And so my final answer is 1 over s. Now for part B, they asked us to find L of e to the power 2t. Again, the same steps. I'm just going to replace all my f of t's with e to the power 2t. I have 0 going to infinity, e to the power minus s of t, s into t times e to the power 2t dt. And again, this is an improper integral, so I need to account for it. So I'll do the same step of limit a tends to infinity, so my integral goes from 0 to a, and then the function inside the integral still remains the same. So e power minus st times e to the power minus 2t times dt. Now, in order to solve this, I can take these functions in common. So like e to the power x times e to the power y is equal to e to the power x plus y. So I'm going to do something similar in this part here. So my next step becomes limit of a tends to infinity with my integral going from 0 to a, e to the power minus st plus 2t times dt. I can then simplify this even further with my integral going from 0 to a, e to the power minus s plus 2t. And just for simplification purposes, I can also take the negative out of the bracket. And so I end up getting limit of a tends to infinity, 0 to a, e to the power negative s minus 2, because I took the negative out of the bracket, t dt. There's a dt here. And now I can just take the integral and I end up getting limit of a tends to infinity minus 1 over s minus 2 times e to the power minus s minus 2 t, and my bounds are from 0 to a. So now I can just plug in my bounds and I get limit of a tends to infinity minus 1 by s minus 2 times e to the power minus s minus 2 times a, minus 1 by s minus 2 times e to the power minus s minus 2 times 0. Now I can just plug my a back in, or a tends to infinity back in, since I've done the definite integral, and I get 1 by s minus 2 times e to the power minus s minus 2 times infinity plus 1 by s minus 2 into e to the power 0. Again, this function here becomes 0, so my first half is 0. Um, and then plus 1 by s e to the power 0 equals to 1. So I'm left with 1 by s minus 2, which is equal to 1 by s minus 2, and that's the final answer for part B. Now, moving on to the next question, it's asking us to determine the behavior of the integral bound, and the bounds are from minus 2 to 14. So just looking at the integral here, or just looking at the function inside the integral, I have this. And when I look at my bounds, I'm looking at the lower bound. So at x equals to minus 2, I get 14 by 4 um, root of minus 2 plus 2, which is equal to 14 over 0, which is undefined. This means that the integral is improper and I need to account for it. So the way I would account for it is essentially limit. And since it's my lower bound, that makes it undefined. I would take it from a tends to negative 2 plus, uh, and the bounds now become a and 14 because uh, my limit is going from my limit tends from a to negative 2. Like my limit of a tends to negative 2. So I just replace my negative 2 with a. And my function inside, I have 14 by x plus 2 to the power 1 by 4. This here can essentially, so 4 x plus 2 can be written as x plus 2 to the power 1 by 4. And this is what I've done in this step. Uh, to make this easier, I would just simplify it a bit. And I would have limit of a tends to negative 2 plus, bounds are still the same, 14 times x plus 2 to the power negative 1 by 4. All I did was bring it from the denominator to the numerator, so I can easily apply the power rule. So now I can do my integral here, and I end up getting limit of a tends to negative 2. So x plus 2 to the power minus 4, we would use the power rule here. So I would get 14 x plus 2 minus 1 by 4 plus 1 divided by minus 1 by 4 plus 1, going from, and the bounds are a to 14. So my simplification, uh, when I simplify, I would end up getting negative 214 times x plus 2. This becomes 3 by 4. Negative 1 by 4 plus 1 is 3 by 4. And my bottom is also 3 by 4, going from a to 14. And I can simplify this further by just taking the 3 by 4 and multiplying 4 on the top. And I end up getting 56 over 3, x plus 2, 3 by 4, from a to 14. Now I can plug my bounds in, and I end up getting limit of a tends to negative 2, 56 by 3, 14 plus 2, 3 by 4 to the power 3 by 4, minus 56 by 3, um, a plus 2 to the power 3 by 4. And now I can plug my a back in since I've done the definite integral. And I end up getting 56 by 3, 16 to the power 3 over 4, minus 56 by 3 minus 2 plus 2 to the power 3 over 4. Minus 2 plus 2 is equal to 0, so my function on the right becomes a 0. So in the end, I'm left with 56 over 3, 16 over 3 by 4. And I can simplify this further. So 16 is equal to 2 to the power 4, and I can plug that back in. 56 by 3 times 2 to the power 4 to the power 3 by 4. And when I multiply, 4 and 4 gets cancelled. I end up having 56 times 8 by 3. And my final answer is then 448 over 3. Now we can move on to the next question, which is asking us to find the area of the region bounded by the curves x is equal to 9y square and x is equal to 2 plus 7y square. So I already have a screenshot from Desmos after I graph the function. It's always good that you can graph the function so you can see which curve is on the right and left or which curve is on the top or bottom, depending on how you decide to solve it. So starting with the formula, the area is equal to um, y1 going to y2 right curve minus left curve dy. So here, my right curve is this blue curve here, which is x is equal to 2 plus 7y squared. And my left curve is this curve, which is x is equal to 9y squared. So I know my right curve and left curve. All I need to do is find my y1 and y2. Y1 and y2 are the coordinates where these two intersect. So on the graph here, they would be this coordinate and this coordinate. And the way we would find it is we would just equate these two equations together. So I'm given that x is equal to 9y squared and x is equal to 2 plus 7y squared. To find those coordinates, I'll just equate them together. 9y squared is equal to 2 plus 7y squared. The reason I can do that is since both of them equate to x, so they both should be equal as well. Now I would just simplify it. I would get 2y squared is equal to 2, y squared is equal to 1, and then y is equal to plus minus 1. So my bounds here now, I get y1 is equal to -1 because that's the lower bound, and y2 is equal to 1. And it's asking us to find the area bounded by these two curves. So essentially, it's looking at this area here. So now that I have all the functions and the bounds that I need, or like the curves and the bounds that I have, all I need to do is plug this back into the formula. So I get area is equal to integral of integral going from -1 to 1, with my right curve being 2 plus 7y squared, subtracted by my left curve, which was 9y squared, dy. And now I'll just simplify this function. I end up getting -1 going to 1, 2 minus 2y squared dy. And then I can simplify this even further by taking 2 common, and I get 1 minus y squared dy. And since 2 is a constant, I'll take that out of the integral as well. And I get 1 minus y squared dy. Now that I have this, all I need to do is integrate that function. So I end up getting 2y minus y cubed by 3. So 1 gives integral of 1 would give me y, and the integral of y squared would give me y cubed by 3 to the power rule. And then I need to take the bounds here from going from -1 to 1. So if I plug in all my values and my bounds in, I get 1 minus 1 by 3. There's 1 by 3, minus of -1, minus of -1 cubed by 3. Now that I simplify this further, I get 1 minus 1 by 3, which is 2 over 3, because 3 over 3 minus 1 by 3, which is 2 over 3, minus -1. -1 cubed gives me -1, and then when I open the bracket with the negative sign outside, I get a plus. And then I can go ahead and simplify this further. I would get 2, 2 over 3, minus 1 plus 1 by 3, so which is minus 3 by 3 plus 1 by 3. So I have -2 over 3. Um, then I have 2 times 2 by 3 plus 2 by 3, which is equal to 2 times 4 by 3, and I get 8 over 3. And that's my final answer, and that's the area bounded by the regions given to us. So now I can move on to the next question. The next question is a word problem. And essentially, they have given that the birth rate, given to us that the birth rate of a population is the function B of t per people per year, and the death rate is the function D of t people per year. And they're asking us to find what the growth of the population is over a 20-year period rounded to the nearest person. So it has given us to us that they want us to find the growth of the population over 20 years. So my bounds for my integration goes from t equal to 0 to t is equal to 20 years. Next, I need to find the growth function. So let's call that our growth function is g of t, and g of t is equal to the birth rate minus death rate. And the reason for this equation is the rate at which you're growing is determined by how many people are born, subtracted by how many people are dying. And in the net, it can be a positive growth. It can also be a negative growth. Um, and given this, we have everything that we need to set up our integral and solve. So our integral would look like t is equal to 0 to t is equal to 20 of g of t dt. And we know that g of t is equal to the birth rate minus death rate. So 0 to 20 minus death rate d of t. Now we can plug in the functions and their values, and we end up getting the bounds of integral from 0 to 20 for 1700 from the values here, 3700 e to the power 0.05t, which is my birth rate value, subtracted by my death rate, which is 1200 e to the power 0.02t dt. Now I can solve for the integral, and I end up getting 3700 times. When I take the integration of e to the power 0.05t, I get 1 by 0.05 times e to the power 0.05t. And similarly, when I do the same for the death rate, I get 1 by 0.02 times e to the power 0.02t. And of course, I need to account for my bounds, which is going from 0 to 20 for this whole function here. My next step is just plugging in those bounds. Or before that, I can also simplify it even further because I can find the value of 3700 divided by 0.05 and the value of 1200 divided by 0.02. So simplification, I get 3000, I get 74,000, which is 3700 divided by 0.05 times e to the power 0.05t minus 60,000, which is 1200 divided by 0.02 times e to the power 0.02t, and my bounds are from 0 to 20 for this whole function. Next, I can plug in the values. So I get 74,000 e to the power 0.05 to the power times 20 minus 60,000 e to the power 0.02 times 20. And then now I have to subtract the lower bound. So I'll just do that on the next line here. I get 74,000 times e to the power 0.05 times 0 minus 60,000 e to the power 0.02 times 0. And when I simplify it, I end up getting 74,000 e to the power 20 times 0.05 is 1. So e to the power 1 minus 60,000 e to the power 0.4. And then I e to the power 0.05 times 0 is e to the power 0, and e to the power 0 is equal to 1. So these two functions, or these two become 1. So I end up getting subtracted by 74,000 times 1 minus 60,000 times 1. Now I can find what e to the power 1 and e to the power 0.4 is in my calculator, and I can replace those values here. So I end up getting 74,000 e to the power 1, which is 2.7182 rounded, minus 60,000 e to the power 0.4 is 1.4918 rounded, minus 74,000 plus 60,000. I've opened the brackets here, so my negative signs get multiplied to both my terms inside. And after simplifying all the values, our final answer comes to be around 97,643.373. And if we go back to our question, it has asked us to round it to the nearest person. So when I round it, I get 97,643 people. And that is my final answer. Now we can go to move on to the next question. So the next question is asking us to find the volume of the solid obtained by bounded by the following functions: x equal to root y, x equal to 3, and y equal to 0, about the line x equal to 3, using the method of disks and washers. So, to begin with, using disks and washer method, our volume, the formula is pi going from y0 to y1, r out, which is my outside radius square, minus rn, which is my inside radius square, dy. So if I already have a photo of the graph here from Desmos. Again, it's advisable to have a graphs. So it's easier to find out what my radiuses are in this question. To begin with, let's just shade the region of the area it's asking us. So that is this region here. We have to rotate it about the line x equal to 3. So this is x equal to 3. This curve here is x equal to root y. Um, and y is equal to 0 is just the bottom line here. So we need our y coordinates to begin with. So let's go down and start finding our y zeros and y ones first. The question has already given me that y is equal to 0. So we need to find the other y. And the way we do it is they have given to us that in the question it's given x is equal to root y, and they have also given that x is equal to 3. So now I just use these two equations and I get 3 is equal to root y. And so y is equal to 3 square, which gives us y is equal to 9. So we have our y0 equal to 0 and y1 equal to 9. So we have our bounds. Next, we have to find what the r out square is and r in square is. So let's go back to the graph. Our r out square, since we're looking about this line, see if I can, yeah. Since we're looking at this line, our r out square is essentially this here. This is our r out. So our r out is 3 minus root y. So I can write r out is equal to 3 minus root y. And r in, since it's asking us to rotate this line, this is our r in, this line here. And this line is just equal to 3. So r in is just equal to 3 minus 3, which is equal to 0. So now we have our r out, r in, and our two bounds. We can plug everything into the formula, and we get b is equal to pi y0, which is 0, going to 9. R out square, which is 3 minus root y whole square, minus Rn, which is 0 squared dy. We can open the brackets. We get pi going from 0 to 9. And when I open the brackets, I get 9 minus 6 root y plus y dy. And when I simplify this, or when I integrate this function, I get pi times 9y minus 4y 3 over 2. And this is all simplified, plus y square over 2. So 6 root y can also be written as 6y 1 by 2. When I do the power rule to integrate it, I get 6y 1 by 2 plus 1, which is 3 by 2, by 3 by 2. And so this can also be written as 4, um, yeah, it can also be written as 4 by 3 over 2. And that's how I got this integral of minus 6 root y. And the bounds are from 0 to 9. So I can plug all my values in and I get pi 9 times 9 minus 4, 9 times 3 over 2 plus 9 squared by 2 minus 9 times 0 minus 4 times 0, 3 power 2 to the power 3 over 2 plus 0 squared by 2. Everything on the right becomes 0, so I'm only focused on this, which is essentially pi times 9 times 9, which is 81 minus 4. I can also write this as 3 square, 3 over 2, and then this and this gets canceled, plus 81 over 2. And when I simplify this function, I end up getting 13.5 pi, which is my final answer. Now, moving on to the next question, it's also the disks and washers method, and it's asking us to find the volume of solid obtained by rotating the region around y is equal to x to the power 1 by 3. So in the graph here, x equal to 1 by, or y equal to x 1 by 3 is this curve. X equal to 8 is this line. And y equal to 0 is the bottom line again. So I'll start by writing my formula, which is volume is equal to pi y1 going to y2 r out square minus r in square dy. I'll also shade the region. So the region bounded is this. And we are rotating it about the y-axis, which is this. Now I need to find what my r out and r in is, and also what my bounds are. So we can first begin by finding our bounds. We already have one bound given, which is y is equal to 0. And given the function on top, which is y is equal to x to the power 1 by 3 and x equal to 8, we can make use of these two and write it as y is equal to 8 to the power 1 by 3, which is essentially cubic root of 8. And the cube root of 8 is 2 because 2 to the power 3 is equal to 8. So 8 to the power 1 by 3 is equal to 2. So now I have my two bounds. So y1 is equal to 0 and y2 is equal to 2. I need to find out my r out and r in square. And to do that, I'll just go back to my graph and draw it all out. So my r out square is essentially all the radius going from here to here, which is just uh so yeah, which is essentially just x equal to 8 because x is equal to 8 here. And then I need to find my Rn. So Rn is this value here, but this is going to be a function because this changes as the curve goes on. And that value is, so we need to find it in terms of y. We know y is equal to x to the power 1 by 3. So x is equal to y cubed. So this is y cubed. And we know that x is equal to 8, so it's just a constant 8. So just to write it all down, r out is equal to 8. and Rn is equal to y cubed. And so now that we have all the required things to plug in our formula, we can just go ahead and do that. So I end up getting volume is equal to pi from y1 to y2, which is 0 to 2, r out square, h square minus y cube square, which is my Rn dy. So I can simplify this further, and I get pi 0 to 2, 64 minus y to the power 6 dy. When I integrate the function, I get 64y minus y7, y to the power 7 over 7, and the bounds are from 0 to 2. So I can now plug my bounds in, and I get 64 times 2 minus 2 to the power 7 over 7, minus 64 times 0 minus 0 to the power 7 over 7. Again, my function on the right-hand side is essentially just 0. It it equates to 0. So I have pi of 128 minus 2 to the power 7 is 128 minus 128 over 7. And when I simplify this, my final answer is 768 pi over 7. And this is the final answer. So now we can move on to the next question, which is to find the volume of the solid obtained by the cylindrical shells method. And the function xy equal to 1, x equal to 0, y equal to 1, and y equal to 3, or the equation. Um, so again, I have the Desmos graph here. I can start the region. So the shaded region, so firstly, this is xy equal to 1. Also, it's color scheme, so you can make sense to that, but I'll just label them regardless. This is y is equal to 1, y is equal to 3, and x is equal to 0. And we need to find the volume through the cylindrical shells. So this is a region bounded by it, and we're rotating it around the x-axis. Or no, that's the y-axis. The x-axis, which will be here. So whenever in cylindrical shells, whenever you rotate about the x-axis, your radius is always y. Um, and firstly, I can just write the formula for the cylindrical shells method. V is equal to 2 pi, going from y naught to y1. Radius, height, radius times height, dy. And like I was saying before, whenever you rotate about the x-axis, like this question has asked, the radius is always going to be in terms of y. So I know my radius is y. I need to find my two bounds, and the two bounds are given in this question as y is equal to 1 and y is equal to 3. So just from the question, y naught is equal to 1 and y1 is equal to 3. And I didn't have to equate any two equations like the previous questions to find that, since it's already given in the question. Next, I have to find my height. Now, since I'm looking at it in terms of the y-axis, my height of the function is actually this. And the way you would find this is by doing like the function on the right minus the function on the left. So r or height is equal to function on out minus the function on in. So the function on out is xy, f out is equal to xy, uh, equal to 1. Since I need everything in terms of like y to be fed into my equation, x is equal to 1 over y. So I have 1 over y minus f in. In is this line here, and that is just x equal to 0. So my height is 1 over y. Now I have all the necessary things to feed into my formula. I can then rewrite my formula as v is equal to 2 pi, y naught is 1, and my y1 is 3, my radius is y, height is 1 over y times dy. And to solve this, y and y gets cancelled. So I have 2 pi y um, with the bounds 1 to 3 dy, which is equal to 2 pi 3 minus 1 dy, which is equal to 2 pi times 2, which is equal to 4 pi. And that's the final volume. Now we can move on to the next question, which is to find the exact arc length of the curve x equal to 1 by 3 times root y times y minus 3 for 1 less than y, for 1 less than equal to y less than equal to 9. To begin, we can first write the formula for arc length, which is L is equal to y1 going to y2, since we're doing it in terms of the y-axis or in terms of just all y's. And then the function is square root of 1 plus dx over dy whole square dy. So we are given x is equal to 1 by 3 times root y minus 3. And our y1 is also given in the question, which is equal to 1, and y2 is equal to 3. Or y2 is equal to 9. So the first step is doing dx, finding this dx over dy. To find my dx over dy, I'll use the product rule. So firstly, I'll just take 1 by 3 common, and then inside I have root y times y minus 3, and I'll use the product rule on this and this. Um, and so I end up getting, so when I differentiate um, square root of y, so dx by dy of square root of y is equal to 1 by 2 root y. So here I have y minus 3 by 2 root y. Because we don't differentiate we differentiate the first function and the second one remains the same. And when we do it, and then we add it to the differentiation of the first term, or the differentiation of the second term multiplied by the first term as it is. So my next term is just going to be root y because my differentiation of y minus 3 is just equal to 1. Now I can simplify this by taking a common denominator. So I have y minus 3 plus root y times 2 root y all over 2 root y. Let me just rewrite that. Y minus 3, 2 root y plus root y times 2 root y. All I'm doing is taking a common denominator here, so I just have it simplified, which ends up being 1 over 3 y minus 3, root y times root y is y, plus 2y over 2 root y. And simplifying it further, I get 3y minus 3 by 2 root y. I can take my 3 common from the top. So I have 1 by 3, 3, y minus 1, 3 times y minus 1 by 2 root y. And my 3 and 3 gets cancelled. So at the end, I'm left with y minus 1, 2 root y. And this is my dx by dy. I need to find dx by dy square. So dx by dy square, which is my next step, and which is equal to y minus 1 by 2 root y whole square. And just squaring the numerator and denominator, I get y minus 1 square by 4y. Because 2 square is 4 and root y square would give me 4y. Next, I need to add this to a 1. So the next step is dx plus dy whole square and just adding it to 1. So I get 1 plus y minus 1 square divided by 4y. And again, I'll do the common denominators here. So I get 4y. I'll expand the y minus 1 square bracket. I get y square plus 1 minus 2y over 4y. And then I get y squared plus 1, 4y minus 2y, which is plus 2y, over 4y. And y squared plus 1 plus 2y is equal to y plus 1 whole square divided by 4y. Now that I have I have found everything under the root, which is 1 plus dx over dy whole square, I can go ahead with the integration. So I get integration of 1 to 9 square root of y plus 1 square for y dy. I can take the square root in and I get y plus 1 divided by, so the square is bottom, 2 root y dy. Um, Next I can just take 1 by 2, which is a constant outside. So 1 by 2, 9, y plus 1 by root y. I can split my numerators, so I end up getting 1 by 2, 1 by 9, y over, I'll write root y as y over 1 over 2, plus 1 by y over 1 over 2 dy. Um, which ends up being, so when I simplify this here, y over 1 over 2, plus 1 by y over 1 over 2, I get 1 by 2 times the integral going from 1 to 9 of y 1 by 2 plus y minus 1 over 2 dy. And my arc length ends up being 1 by 2 times, so now I'm just doing the integration using the power rule. I get 2 over 3 y times 3 over 2 plus 2y to the power 1 over 2 going from 1 to 9. And I can plug in my numbers here. I get 1, 2, 2 by 3, 9 times 9 to the power 3 over 2 plus 2 times 9 to the power 3 over 2 minus 2 by 3, 1 times 1 to the power 3 over 2 plus 2 times 1 to the power 1 over 2. And when I simplify all of this, I get L is equal to 1 over 2 times 64 over 3. And my final answer is then 32 over 3. And that's the arc length of the function. Uh, the next question is a word problem. It's so there's a drone that's traveling due west. The drone's height above the ground from the position x equals 0 to x equal to 30 meters is given by the following function. What expression represents the distance traveled by by the drone? Again, we can use the arc length formula here. But this time it's in terms of x, unlike the previous question, which was in terms of y. So in terms of x, the arc length formula is x1 minus x2 of root 1 plus dy over dx whole square times dx. Okay. They have given us to us that x1 is equal to 0 and x2 is equal to 30. Um, y is given as 100 minus 1 over 20 x minus 30 square. So I need to find dy over dx. So dy over dx, which is equal to, so the differentiation of constant, which is 100, becomes 0. And the term on the right, we we get minus 2 over 20 x minus 30 to the power 1, 2 minus 1, which is equal to minus 1 by 10 times x minus 30. Next, we need to do dy by dx whole square, which is equal to minus 1 by 10 times x minus 30 whole square, which is equal to 1 by 100 times x minus 30 whole square. And the question is just asking for the expression. And we have everything to just fit in that formula. It's not asking us to find what the arc length is. So then when we plug in all the necessary values, we get the integral going from 0 to 30 from 1 um, for square root of 1 over dy by dx whole square, which we found was equal to 1 by 100 times x minus 30 whole square dx. And this expression is the final answer. Next up, we have a word problem. The word problem says that there is a cylindrical tank that is standing on a circular base with a radius of 4 meters and a height of 7 meters, using 9.8 meters per second squared for acceleration due to gravity and 1000 kg per meter cube as a density of water. Set up the integral for the work required to pump the water out of the tank. And then they have given us four scenarios. Um, the first scenario is the tank is full of water and it's being pumped out of a spout at the top of the tank. Part B is just half full of water and it's being pumped out of a 0.75 meter long spout at the top of the tank. C is the tank is full of water. We don't have any spouts now, and it's just being pumped from the top of the tank. And part D is the tank is full of water, but we just want to pump half of the water out of the tank. So, first, let's just start with a part A and draw a cylinder to kind of see what it's asking. It's saying that the height, and this, let's just say it's sitting on a X and Y axis here. It's given that this is 4 and the height is, so this is 0 and this is 7 because my whole height is 7. That's my cylinder. And it's saying that it's full of water. So this is all water, and there's a spout on top of the tank, which is throwing out the water. And the height of the spout is 0.5 meters. Um, so to basically find the work, we have to multiply the given acceleration, gravitational acceleration times the density, which is already given to us, times the area of cross section, times like the variable height that we're trying to throw out the water from, or that'll be left in the tank in the end. So we can start by doing a cross section, area of the cross section. So if I just take an arbitrary thin slice here, let's say this is my thin slice, the area of this thin slice is equal to pi r square because that's the area of the circle and it's a cylinder, so it's just going to be pi r square. The radius is given to us as 4, so pi times 4 squared, which is equal to 16 pi. Um, so now let's just state what's given to us. It's given that top of tank, y is equal to 7, and top of the spout, so the vertical spout. Here y is equal to 7.5 because it's 0.5 from the top of the tank, so we need to do 7 plus 0.5 just based on the coordinate system that we have set here. Um, so the distance that the water is lifted, which is going to be some distance here, that the water is just going to be lifted as, and it's going to be lifted through all of this. So it's lifted from the whole of 7.5, but sometimes, like let's say the water is only half full or less full. So then here or water might be here, I need to subtract my y from it, or this y from it. So if I have to draw this out for more better reasoning, let's say they have given to me that the tank is full, but let's say at a point that I'm throwing the water out, the water is only this much left in the tank as I'm throwing the water out. And this is 7.5, but I'm lifting it for y. Like essentially my work done is only for this part, and this is y. So the distance lifted ends up being 7.5 minus y. Um, so now I can set up my integral. They're not asking us to solve the integral. So when I set up my work, it's the integral going from 0 to 7. It's from 0 to 7 because my whole tank here is only from 0 to 7. So all the water that I have is only from 0 to 7. I'm integrating essentially every thin slice of the circle. And as a result, it can only go from 0 to 7 and not from 0 to 7.5. Next, I multiply the gravitational acceleration, which is given, times the density, which is also given, area of cross section, which we found out as 16 pi, times the distance the water has been lifted, which is 7.5 minus y times dy. And this is part A. Next, we can go to part B. Part B is saying that the tank is half full of water and it is being pumped out of a 0.75 meter long vertical spout at the top of the tank. So now in the cylinder, my water is only half full. So it's only up until here. Um, and I know that this part is 0. My radius is still 4. So my cross section is still 16 pi because my radius is not changing. But here, the only amount of water I have is from 0 to 3.5. Unlike the previous question where we had it from 0 to 7, we will now just be integrating over the bounds from 0 to 3.5. But first, let's just find out the distance that the water needs to be lifted. So it's given top of tank, which is y is equal to 7. Um, Top of vertical spout, which is y is equal to 7.75, because in this question, this is 0.75 and this is 7. So the vertical spout is all the distance. Based on a coordinate system, it's sitting. So I'm calculating the top of the spout, which is then 7 plus 0.75. And now I can set up my work function as work is equal to the integration from 0 to 3.5, because I only have half the water now, times, or inside the integral, I have the gravitational acceleration times the density times the area of cross section and the distance that it's lifted. So the distance water is lifted is um equal to 7.75 minus y, because we are lifting it. Like if my water is here, it might get lifted from here, and this is y. So I just need to do 7.75 minus y to find the actual work done. 7.5 minus y times dy. And this was my part B. This is the final expression for part B to find the work done. Next, part C. Part C is saying the tank is full of water and it is being pumped out over the top of the tank. So in this part, I have a cylinder. Again, same other, but however, it's like part A, but there's no vertical spout anymore. This is 7 and my radius is 4. And the 7 is just sitting on the y coordinate. So now it's asking to find the work done of just pumping out the water from the top of the tank. So top of tank is y is equal to 7. And the distance the water lifts now, or the distance essentially to find the work done, water lifted, is just 7 minus y. There is no more spout on top here. So it's just from the top of the tank, and the topmost part of the tank is sitting at y is equal to 7. Now I can find my work, the integral expression for my work. So this is bounded from 0 to 7 because my tank is full, so I need to account for all the thin slices going from 0 to 7. Um, inside the integral, I have gravitational acceleration times the density times the area of cross section times the distance lifted, which is 7 minus y times dy. And this is the final work expression or the integral for part D. For part C. For part D, the tank is full of water, but you just want to pump the half water out of the tank out over the top of the tank. Okay. So I'll just draw the cylinder again. I have this. It's only asking for the top half of the water, so I'm only going to draw the top half of the water here. We just the top half, so this part, the topmost part is 7. The half is 3.5. Again, the distance the water is lifted is still like 7 minus y because I can have y here and I'm lifting it from here. So I still need to subtract y from it. Like the tank is still full, but I'm only worried about the top half part of it. So then my work expression in the end ends up being work is equal to, it's not 0. So it's not 0 anymore. Since I'm only worried about the top half part, it's going from 3.5 to 7 because I'm only looking at the thin slices from this half and up. Inside the integral, we have the gravitational acceleration, density, the area of cross section multiplied by the distance lifted. Like I said, the distance lifted is still the same. Um, but since our integration just accounts that it's only going to look at the top half part of it, dy. And this is the final work expression for part D. Next, we have another word problem. And this word problem says, consider a saltwater aquarium in the shape of a rectangular prism with a base of length 3 meters, a height of 1.5, and a width of 2. Using g for acceleration, due to gravity, and the density, set up integral for the work required to pump the water out of the tank if the aquarium is full of water and it is being pumped out over the top of the aquarium. And part B is asking if aquarium is full of water, but you just want to pump half the water out of the aquarium over the top of the tank. So it's pretty much like the previous question, like very similar to it, except that instead of a cylinder, we have a rectangular prism. So let me just draw that out. Yeah. And this is for part A. It is given to us that our base length, base of length is 3 meters. So I'll draw my coordinate axis as this, just to make things much easier. So it's given that the base of length is 3 meters. So this is 3, the width is 2 meters, and the height is 1.5. Um, and it's full of water. So it's filled with water all the way. Oh, I don't know why it's erasing it. I can just redraw that real quick. It's full of water. The bottom was 2, 3, and the width was of 2. And it's being pumped out over the top. There's no vertical notch here. And Yeah, so we just need to find out the work done. We are given that G is 9.8 and our density is 1030. We need to find the area of cross section. So if I just draw it here again, just draw this real quick. This being my rectangular prism, and my area of cross section is essentially this part here. So if I shade it, it looks something like this. And to find my area of this, all I have to do is multiply um this times this, because it's essentially just a rectangle. So my area, which is, let's just say that's L, and this is my width, is L times W, which is equal to 2 times 3, which is equal to 6. It's 1.5 meters. Again, the same concept for the distance lifted for the water. So, the top of the tank is 1.5 meters. So to lift all that water, the distance to lift water is going to be equal to 1.5 minus y. Now I can just set up my work, the integral for my work done, which is equal to 0.0 to 1.5. Because my height is 0 to 1.5 and I need to integrate over all the thin slices of the cross sections I'm cutting in my aquarium, which is filled with water. Um, and inside the integral, I have my gravitational acceleration, which is 9.8, density, which is 1030, times area of cross section, which is A, and then the distance the water is lifted, which is 1.5 minus y dy. And this is my work expression for part A. For part B, the question is asking, or the question states that is asking for the work done only for pumping the half the water out over the top of the tank. So if I draw my rectangular prism again, got this, it's only looking for the top half of the water. So I can like draw something like this. My area of cross section, there's still water all over the aquarium, but we're only looking at the top half. So the top half goes from 0.75 to 1.5. Um, my area is still the same, which is 2 times 3, because the cross section stays the same. It's not changing in this question. So area is still 6. The only thing that changes here are my integral bounds. But before accounting for my integral bounds, let's just find what the uh distance for lifting the water is. The distance to lift water, it's still going to be equal to 1.5 minus y. It's the same reasoning as the previous question. There's still all the water in the tank, but if your water is here and you're trying to like lift it to the top of the tank, you still have to do the whole height minus y here. Um, so yeah, now that we have that, we can start writing the integral for our work, which goes from 0.75 to 1.5, because we only want to pump out half and the top half gets pumped out first. Um, Inside the integral, we have our gravitational acceleration, our density of water, times the cross section, times the distance the water is lifted, dy. And this is the final expression for part B. For the next question, it's asking us to describe the behavior of the sequence an is equal to 5 to the power n plus 2 divided by 6 to the power n plus 2. So to find behavior of sequence an, we find it using the formula limit of n tends to infinity a of n, an. So this is now equal to limit of n tends to infinity. We just replace a of n with the function, or not the function, the term that was given to us. So 5n plus 2 divided by 6 to the power n plus 2. So limit n tends to infinity. So both my numerator and my denominator have the same power. So I can write this term as 5 by 6 to the power n plus 2. And here, 5 by 6 is less than 1. And whenever it's less than 1 and my limit n goes to infinity, um, it's just going to, like, the whole term is just going to be 0. So for example, I had 0.1 to the power n of n tends to infinity. Let me just rewrite that. So limit n tends to infinity of, let's, for example, 0.1 to n. So 0.1 to the infinity would give us 0. And this is because it's less than 1. And whenever the term inside here, it's less than 1, our limit or anything to the power infinity would always tend to 0. So similar thing here, since 5 by 6 is less than 1, the limit of n tends to infinity would tend to 0. So if I just have to rewrite it, I have 5 by 6 to the power infinity plus 2, which can also be written as 5 by 6 to the power infinity. And this tends to 0. This just goes to 0. So it goes to a certain value. So we describe the behavior as converges, and it's converging to the value 0. So a whenever it says converging, that means it should always point to a singular value. Whenever it says diverges, it's either going to infinity or it's undefined. And converges to 0 is the final answer for this question. The next question is asking us to describe the behavior of the series of the same function as the previous question. So, yeah. So the way you would solve it is you want to get it down to geometric series. And usually geometric series is written in the form of, so geometric series is equal to a r n minus 1. Like essentially it's the sum of all of it. So like say it's actually going from n equal to 1 to infinity. And if we can get this function down to this form, our sum of geometric series, so which is a sum of each and every term inside, is equal to a by 1 minus r when when the modulus of r is less than 1. If it's greater than 1, it's going to converge. It's just going to go to it's going to diverge. It's just going to go to infinity. So to write the function which was given to us, or the term that was given to us, n equal to 1 infinity, um 5 by 6 to the power n plus 2. Same thing. It's the same question as above, since they both share the same power. I can just take the numerator and denominator as common to the power of whatever is given. I need to get it down. So I can also write this down as n equal to 1 infinity 5 by 6. I can write plus 2 as minus 1 plus 3. So it's 1 plus 3. And plus 2 is just minus 1 plus 3. And all I'm doing is just replacing it for this value here. Next, 1 infinity, I can write this as 5 by 6 to the power 3 times 5 by 6 to the power n minus 1. And what I did here is, let's say I have a to the power 2 times a to the power 3. I can write it as a to the power 2 plus 3, which is then equal to a power 5. All I'm doing is back stepping from this. So if I have a to the power 2 plus 3, a to the power 2 plus a to the power 2 plus 3, I can also write it down as a squared times a cubed. This is all I've done in this step. And the reason I'm doing it is to get it in this form here, which is AR to the power n minus 1. Now that I have this, it's in the form of geometric series. My modulus R is equal to 5 by 6, which is less than 1. So we know it converges to a value, and we can find, or the sum of the series is going to converge. A is equal to 5 by 6 cubed. So to write this down, this is A R to the power n minus 1. Next, I can, going back to this formula sum of geometric series, I can do sum is equal to A by 1 minus R. A is equal to 5 by 6 whole cube divided by 1 minus R, which is 5 over 6. So to simplify it further, 5 cube is 125 divided by 6 cube, which is 216, divided by 1 minus 5 over 6, which is equal to 1 over 6. And when I simplify this further, I get 125 over 36. And this is the final behavior. So this is what the sum is going to converge to. And it's converging to this value of 125 over 36. And this is the final question for the review. If you have any other questions, please feel welcome to come to the FSC Tutoring Center, which is located at ECG 152. And any of the math tutors can help you out, whether it's a question with your homework or in this exam review, or you just need more practice problems. You can always come to the Tutoring Center for help. And thank you for seeing this review.